Section 3.5, Additional Integration Techniques. Our objectives are 1. Integrate using integration by parts, and 2. Use integration by parts combined with U substitution and other strategies. Note, we're not covering integration by tables. It's not in our course objectives, and I know all of you can follow a formula and substitute the appropriate pieces. Integration by parts formula. For indefinite integrals, the integral of u dv equals uv minus the integral of v du. The idea is to take something that we can't integrate directly with the formulas we have and cleverly select the pieces so that we can integrate. For definite integrals, the integral from a to b of u dv is uv evaluated from a to b minus the integral from a to b of v du. So let's do an example. When I look at this integral here, frequently if I see an e in there, I put it in the dv part. So I'm going to let u equal x and dv equal e to the x dx. So here then du would be dx and v would be the integral of e to the x dx, which is e to the x plus c. Now we're not going to throw in the c's until we need to. So now we can do our substitution. Our integral x e to the x dx, this is my u, this is my dv, equals u v minus the integral v du. Du was dx, exactly what I needed. So that would be x e to the x minus, but the integral of e to the x dx is e to the x. And now we'll put on our plus c. And that's it. Now understand, the problems are rigged so that you can solve them. So you will get the pieces that you need. Guidelines for integration by parts. You want to choose u and dv so that du is simpler than u and dv is easy to integrate. So like I mentioned in the previous example, frequently if I have an e to some power, I will select that to be the dv. Now just to remind you what the formula is where we can see it. So the integral of u dv is uv minus the integral of v du. So I see here I've got 7x e to the 2x dx. I'm going to just select that to be my dv and this to be my u. Notice that if u is 7x, du is 7 dx, it is indeed simpler because I don't have the variable anymore except for the differential. And if I let dv equal e to the 2x dx, then v is the integral of e to the 2x dx. And to integrate this, we're going to have to go ahead and use a u substitution. So I'm going to let u equal 2x, then du would be 2 dx. So du over 2 would be dx. And this allows me to do then the u substitution to integrate this v. So v would be the integral e to the u du over 2 I'm going to continue this down here. So that would be 1/2 e to the u du, which would give me 1/2 e to the u plus c, which would give me 1/2 e to the 2x plus c. So remember what we were solving here is we were finding v. Let me just make sure that looks like a 2. So now I have all the pieces that I need to substitute into here. So u is 7x, v 1/2 e to the 2x. So I'm going to put the 1/2 out here, e to the 2x, minus the integral of v 1/2 e to the 2x, du 7 dx. So 7/2 x e to the 2x minus, I'm going to pull out all of these constants, so 7/2 times the integral e to the 2x dx, which I already solved this integral because e to the 2x dx we already found was 1/2 e to the 2x plus c. So 7/2 x e to the 2x minus 7/2 times 1/2 e to the 2x plus c. So 7/2 x e to the 2x minus 7/4 e to the 2x plus c, and we are done. If a logarithmic expression is present, we usually select that part for u. If not, we usually select an algebraic expression like x or dx for u. So remember, here's what we're looking to sub into. The integral of u dv equals uv minus the integral of v du. Here I have a logarithmic part, so I'm going to let u equal ln x. Then du would be 1 over x dx. So dv has to be whatever is left, so that would be x dx, which means that v is the integral of x dx. So that would be x squared over 2 plus c. So now let's sub back in here. U ln x, v x squared over 2. I'm going to put that in front just because we usually write multipliers of logarithms in front of them, minus the integral of v x squared over 2 du. But this is going to simplify nicely. So I've still got x squared over 2 ln x minus the integral of x over 2 dx. So now I'm going to pull this constant out, and now I'm ready to integrate that. And now I can simplify. And we're done. Other strategies. If you try and integrate by u substitution and you find you have a leftover variable, you may be able to divide and integrate in a different algebraic form. In particular, this strategy works if you have the same degree in the numerator and the denominator. Here's an example of this strategy. When I go to integrate this, if I let u equal 3x plus 5, then du would be 3 dx. And I can't integrate this by parts because I don't have anything to deal with this x here. So what I'm going to do is divide this out and change it into a different form. So if I take 3x divided by 3x plus 5, that would be 1. And we do this division automatically. Remember what you do. You then subtract, and we would get negative 5. 3x minus 3x is 0. So that tells me that 3x over 3x plus 5 is 1 minus 5 over 3x plus 5. So we're going to change the form of this integral first. So this would be the integral of 1 minus 5 over 3x plus 5 dx. And now I'm going to separate that out. So that would be the integral of 1 dx minus 5 times the integral of 1 over 3x plus 5 dx. And now I'm going to have to use the u substitution for this part, but it's going to work this time. So what I'm doing is I'm letting u equal 3x plus 5, then du is 3 dx. So du over 3 is dx. And let's just leave this part alone for a minute. So I can put the u substitution here, and now I want to pull out this constant. So this would be the same as the integral of 1 dx minus 5 thirds, the integral of 1 over u du. And now I have something that I can easily integrate. So that would be the integral of 1 dx is x minus 5 thirds ln absolute value of u plus c. And now I can substitute back in from my u up here. So that would be x minus 5 thirds natural log absolute value 3x plus 5 plus c. And we're done. Now let's find an integral where we need to use integration by parts and the strategy above. Now let's find an integral where we need to use integration by parts and the strategy above. So remember, our goal is we want to take the integral of u dv equals uv minus the integral of v du and cleverly select u and dv to make this something that's easier to integrate. So again, when we see a logarithmic component, that is a good choice for u. So let's let u equal the natural log of 8x plus 3. Then du would be 1 over the argument, and the numerator would be the derivative of the argument. And once we use that for u, then what we have left for dv is dx, and that tells us that v is x. So let's go ahead and do our substitution here. So the integral of the natural log of 8x plus 3 dx would be u v is x. I'm going to write it out front because that's how we usually write it, minus the integral of v du. Now I'm going to go ahead and rewrite that. That would be x natural log of 8x plus 3 minus the integral of 8x over 8x plus 3 dx. And again, if we try integration by parts, we're going to see that we have this leftover piece here. So we're going to go ahead and do the long division and change the form of this piece. So if I take 8x divided by 8x plus 3, that would be 1, and we subtract to see what we have left, and what we have left is negative 3. So 8x divided by 8x plus 3 is 1 minus 3 over 8x plus 3. So now I'm going to rewrite the integral here as x ln 8x plus 3 minus the integral of 1 minus 3 over 8x plus 3 dx, and I'm going to rewrite this, so x ln 8x plus 3 minus the integral of 1 dx minus plus the integral of 3 over 8x plus 3 dx. And you can see we could pull this out. So I'm going to do that. And now we want to go ahead and use u substitution to do this piece. So if u is 8x plus 3, du would be 8 dx. So du over 8 would be dx. So let's go ahead and put in that. So x ln of 8x plus 3 minus the integral of 1 dx would be x plus 3 times the integral 1 over u du over 8. So that gives us x ln 8x plus 3 minus x plus 3/8 times the integral 1 over u du. And finally, we're getting to the point we can integrate, so we've got x natural log of 8x plus 3 minus x plus 3/8 natural log of the absolute value of u, which is our u here, 8x plus 3, plus c. Now notice at the very beginning of the problem we were given the natural log of 8x plus 3. So it was already assumed that this was a positive value. So at that point, that's why we are allowed to write this as x natural log of 8x plus 3. We're already using this expression. Minus x plus 3/8 natural log of 8x plus 3, again, plus c. And we're done. Example 6. Find the integral of the square root of t to the 5th power, ln t. So remember, what we're looking for is cleverly selecting u dv so that we can take u v minus the integral of v du. And we said whenever we have a logarithmic part, that's a good choice for u. So u would be ln t, so du would be 1 over t dt, and that leaves our dv to be t to the, remember, square root is a fractional exponent, so t to the 5 halves dt. So v would be the integral of t to the 5 halves dt. And that would be 2/7 t to the 7 halves plus c, but we'll add that part in when we get to the end. So now I can sub in to my formula up here. So I've got u ln t, v, I'm going to go ahead and put this out front, 2/7 t to the 7 halves minus the integral of v 2/7 t to the 7 halves du. Du is 1 over t dt. But we can put these parts together. Remember that 1 over t is t to the negative 1. So this would be the same thing as 2/7 t to the 7 halves natural log of t minus the integral of 2/7 t to the 7 halves t to the negative 1 dt, which we can then put together. So we have 2/7 t to the 7 halves natural log of t minus, and I'm just going to go ahead and pull this 2/7 out, the integral of t to the 7 halves times t to the negative 1 would be t to the 5 halves dt. And now this is going to be a piece of cake to integrate. So we have 2/7 t to the 7 halves ln t minus 2/7 times the integral of t to the 5/2, that would be 2/7 t to the 7/2 plus c. Put it all together, 2/7 t to the 7/2 ln t minus 4/49 t to the 7/2 plus c. And we are done. Now we're going to do an example of using integration by parts for a definite integral. We'll follow the same basic rules, but we'll evaluate from a to b when we get to the end. So again, I've got a logarithmic part here, so I'm going to choose that to be my u. So let's let u equal ln x, then du would be 1 over x dx, and what I have left has to be my dv. So dv would be 3x squared dx. So v would be the integral of 3x squared dx, and that would be 3 times the integral of x squared dx, and that would be 3 times 1/3 x cubed plus c. So v is x cubed plus c. So now we can go ahead and do our substitution. So uv would be ln x is u, v x cubed, we'll put it out front because I've got a natural log here, evaluated from 1 to e minus the integral from 1 to e of x cubed, that's my v, du. du is 1 over x dx. So now I'm going to simplify. So I've got x cubed natural log of x evaluated from 1 to e minus the integral from 1 to e of x squared dx. So we continue, x cubed natural log of x evaluated from 1 to e minus x cubed over 3 evaluated from 1 to e. So let's go ahead and do the evaluation. That would be e cubed ln e minus 1 cubed ln 1 minus e cubed over 3 minus 1 cubed over 3. So remember, ln e is 1. So that gives us e cubed minus 1 times the natural log of 1 minus e cubed over 3 minus a third, so plus a third. And this, we can go ahead and estimate the value using our calculator. So that would be e, that's the second function of natural log, gives you a power of e to the third power minus the natural log of 1 minus the minus e to the third power divided by 3. You really have to watch your parentheses here, plus 1 divided by 3. and that gives us our value. And I'm going to go ahead and go to 5 decimal places just in case. So 13.72369. So approximately 13.72369. So now you know how to integrate by parts and integrate by parts when you need to use some other strategies as well.